The awesome power of the nuclear explosion has been harnessed and is being used to benefit all our lives. Nuclear power plants fueled with uranium are already producing electricity for millions of Americans, and many more of these plants will be built in the future. Our country is dependent upon the uranium industry and the uranium miners for a continuing adequate supply of this magic element. The magic of uranium stems from its property of radioactivity. It is this same property, however, that endangers the health of workers who mine and handle uranium. Therefore, special precautions must be taken to protect uranium miners from exposure to excessive radioactivity. That's what this film is all about. The property called radioactivity means that individual atoms decay at a certain rate and emit energy in the process. Each decay event results in a breakdown of the original atom into an atom of a different element and is accompanied by a characteristic release of energy. Beginning with its change to thorium-234, each atom of uranium is transformed in steps through 13 elements before becoming a stable atom of lead. One element in this uranium decay series is a gas called radon. Thus, radon is being gradually formed in all uranium-bearing rock. Being a gas, radon can seep into the mine air from rock surfaces and cracks exposed by mine openings. Normal radioactive decay of radon then continues in the mine atmosphere. Radium A, radium B, radium C, and radium C prime are the elements which immediately follow radon in the decay series. Although decay continues beyond radium C prime to stable lead, the latter changes require much more time. The first four daughters of radon are believed to pose the principal threat to the health of uranium miners because they result in a relatively rapid release of alpha energy. When a mixture of radon and its daughters is inhaled, most of the radon atoms are exhaled before they have time to decay. However, many radon daughters are retained in the lungs, where their decay and release of alpha particles can damage living tissue. The hazard is, therefore, more directly related to the radon daughter concentration in the mine air than to the radon gas concentration. About 1921, an early suspicion of the danger of radiation from radon and its daughters came from Europe, where uranium and radium were being mined. In one district where radon daughter concentrations were very high and mine ventilation was poor, about half of the deaths among underground miners was from cancer. Records are not available, but it is assumed that early American uranium miners had a similar exposure to radon daughters. Studies by the U.S. Public Health Service indicate that radon daughters can be a health hazard in the form of lung cancer. When the serious nature of the hazard in American mines became known, action was taken to improve ventilation. the most effective known defense. The standard method of measuring concentrations of airborne radioactivity is by filtering the radon daughters from a specific volume of air and counting the decay events on the filter paper with a detection device. The result is converted to working levels. One working level is defined as any combination of short-lived radon daughters in 1 liter of air that will result in the ultimate emission of approximately 130 billion electron volts of alpha energy. Exposures of individual workers are expressed in working level months. This provides an estimate of the radon daughters inhaled during a month. A miner exposed to 5 working levels for 200 months has received 1,000 working level months of exposure. Although medical findings indicate that the incidence of lung cancer among uranium miners increases greatly above 1,000 working level months, there are enough recorded cases at less than 1,000 working level months to indicate that some risk also exists at lower exposures. One working level, for long periods of time, was considered the maximum average level to which man should be exposed. More recent health data has prompted some authorities to recommend that the Radiation Protection Guide for long-term exposure be no more than 4 working level months per year. The highest incidence of lung cancer has been observed among uranium miners who are believed to have worked in concentrations above 10 working levels for 10 or more years. This incidence of cancer also appears to be related to cigarette smoking. Very few non-smoking uranium miners have contracted lung cancer. Therefore, it is recommended that uranium miners do not smoke. Radon and its daughters are also found in other mines, but usually in low concentrations. They may be present in any underground excavation where minerals containing uranium or radium are present in the rock formations. The first concern in the radon daughter control program should be proper mine planning to limit the contamination of mine air. The less radon and daughter products allowed to enter air currents upstream from occupied mine areas, the less ventilation and other measures are required. The erection of seals can limit contamination from areas previously mined on the advance. Seals can also prevent short-circuiting on intake air. Seals should be airtight. They must be built to withstand concussion from blasting, and they must be made of or coated with materials that will retard the passage of radon gas. Urethane rigid foam, asphaltic materials, and certain plastic films have proven to be effective coverings or coatings for seals. A reduced pressure behind seals will prevent contaminants from leaking into active areas. Suction by a surface fan exhausting from a hole drilled into the sealed area reduces the pressure. Even with good planning and use of seals, some radon and its daughter products will enter active areas. The most effective way of controlling this problem is by means of conventional ventilation. For adequate control, it is necessary to have fans capable of providing plenty of fresh air to all work areas. Proper air distribution requires advanced planning. The primary or main ventilation system handles the total volume of air exchanged between the surface and underground workings. Auxiliary fans direct air to active mining areas, such as stopes or dead ends, which are not reached by primary air currents. Well-designed and installed mechanical ventilation systems are a necessity for radon daughter control. But unless these systems overcome natural draft effects, fresh air volumes may not be adequate and air reversals, accompanied by a rapid buildup of radon daughters, may take place. The total volume of air required varies with the type of operation and the degree of contamination. The primary air supply must always exceed the combined auxiliary fan capacities. Otherwise, recirculation will occur. In all but the simplest ventilation systems, doors, stoppings, or regulators are needed to control the flow of air. These components are often as vital as the fan itself. Doors left open or damaged and faulty stoppings make the difference between a safe atmosphere and one which can be a serious threat to health. Changing a regulator or opening a door can result in short-circuiting air intended for another work area. Auxiliary ventilation systems are an aid to the primary systems. It is essential that they be correctly installed and maintained. Stopes and headings are often impossible to ventilate without auxiliary fans. The auxiliary system must pick up air from the primary system and move it into the mining areas. Miners ordinarily spend most of their time in face areas. Hence, proper ventilation in such areas is vital. An auxiliary fan with vent tubing is the most common way of delivering air to working faces. Auxiliary systems may operate in different ways. Both metal and plastic tubing are used. Each type has certain advantages and disadvantages. The blowing system is common in uranium mines. The application of a fan blowing air through a tube seems simple. However, studies of ventilation effectiveness show that auxiliary systems can be critical sources of trouble if they're not properly installed and maintained. Ventilation problems fall into two major categories. The first is the delivery of adequate volumes of fresh air to effectively sweep radioactive contaminants from the face area. The other problem is that of maintaining the quality of air discharged into the work area. Even a very small amount of radon daughters in the intake air greatly increases the air requirements. As contamination of the air delivered approaches the maximum recommended concentrations, control by ventilation becomes more and more difficult. Here, larger tubing was required and installed. To assure adequate air quantities, proper fan selection is important. The fan must produce sufficient pressure to overcome the maximum system resistance and to satisfy flow and volume requirements. Because system resistance changes with the length and diameter of the tubing, the fan should be compatible with current and projected mining plans. Tubing type and diameter affects system resistance and the amount of leakage which occurs. Leakage reduces the amount of air delivered to the working place. Oversized tubing, for example, may be more easily damaged. This susceptibility to damage may offset the advantage of greater airflow and lowered system resistance. Selection of metal or plastic duct should be based on practical considerations. Metal ducts are more durable. However, adapting them to irregularities along the mine opening may be more difficult. Leaks around joints are a common problem encountered when using metal ducts. Ends may be damaged when ducts are stored or moved, and joints may leak after they are connected. Taping joints is one way to minimize leakage. Plastic tubing, while flexible, is more easily damaged than metal ducts. Unless plastic tubing is properly suspended, it may kink and get out of alignment, thereby increasing the resistance. Tubing should be hung and supported to minimize distortion. Messenger wires or slings can be used for this purpose. Sharp turns result in kinking. Therefore, elbows should be used where sharp angle turns cannot be avoided. To help protect against the health hazard from airborne silica dust, air-water sprays may be needed in face areas during and immediately following blasting. Blasting is a common cause of tubing damage. When the rock is naturally dry, wetting it at both face and or transfer points is necessary. Fly rock can be thrown many feet from the face. Metal and plastic ducts are often ruined in this manner. Tubing ends can be pulled back out of the way at blasting time if a pigtail hung from a messenger wire is provided. The discharge velocity of air should be sufficient to sweep the face. The maximum distance that air can be expected to travel from the end of tubing is about 25 feet. Tubing ends must be kept within this distance from the face, and the air must be directed at the workers. Holding down tubing ends with rocks or tying them with wire restricts the airflow. Air discharged from tubing at high velocities into large stopes may rapidly draw contaminated air into the moving airstream. This often results in the air quickly losing its dilution capacity, only a short distance from the end of the tube. One way of obtaining greater dilution in the working area is by diffusing the discharged air close to the men in all directions through a section of perforated tubing. However, this practice restricts airflow and reduces air volume delivered by the fan. Therefore, it is recommended only when there is an abundance of air. Recirculation of air within individual and between multiple auxiliary systems should be avoided. When used air from one system enters the intake of another, the second system will receive pre-contaminated air and may not protect the men. Smoke clouds can often be used to detect where recirculation is occurring. Whenever possible, all fan inlets should be located 8 to 10 feet upstream from the first entrance of return air into the air course. Where it is impractical to prevent all recirculation, the primary air current must be adequate to dilute to safe limits the recirculated air. Constant maintenance is an important requirement for auxiliary systems. Leaky or damaged sections of tubing or ducts should be repaired or replaced promptly. Where primary air becomes too contaminated to use for auxiliary systems, the capacity of the primary system must be increased, or the auxiliary fan inlets moved closer to fresh air sources. If an auxiliary system is operating near capacity and a further increase of air volume is needed, inline booster fans may be utilized. Booster fans are often the best way to increase air volume flow through tubing. High pressure leakage can be minimized by proper location of booster fans. Auxiliary systems must be checked regularly by measuring and comparing the intake and discharge air volumes. When leakage becomes excessive, the condition should be remedied. If the radon daughter level in the working place is not being controlled, a sample taken at the fan inlet or tubing discharge end will indicate that improvement of intake air quality or quantity is needed. Filtration units are sometimes attached to auxiliary systems to temporarily cleanse intake air of radon daughters. Such units do not remove radon gas. Therefore, daughter products may redevelop in the filtered air quickly, depending upon the amount of radon present. Because of the radon buildup factor, it is usually impractical to recycle air through filtration units. Air quantities necessary to adequately ventilate working areas vary with the size of opening, the amount of ore exposed, and the inflow of radon and its daughters from adjacent areas. Experience indicates that 2,000 to 3,000 cubic feet of uncontaminated air per minute delivered in each production heading will usually control radon daughter concentrations to acceptable levels. The quantity of air delivered should cause an air change in the working areas about every 4 to 5 minutes. Ventilation should be the concern of everyone who works in a mine. Fans and other ventilation controls are installed to ensure that an atmosphere is provided which does not endanger health. Misused or damaged ventilation components can result in hazardous health conditions for everyone working in the affected area. Fans should be operated continuously while men are underground. When a fan is not running, radon daughter concentrations in mine air will build up rapidly. Preferably, fans should be operated 24 hours a day. Where this is not practical, they should be restarted soon enough to reduce radon daughter levels to recommended values before men go underground. The best way to determine the time needed to reduce this level is to take radon daughter samples at key locations after fans are started. Even under the best conditions, there may be times when men must enter poorly ventilated areas. In recognition of this problem, the Bureau of Mines has tested and approved respirators which should be worn for protection against radon daughters where environmental control is impractical. However, respirators are only recommended for short-term use and not as a substitute for practical control measures. Also, proper fitting and maintenance are a must if respirators are to fulfill their intended purpose. Here, a split system of ventilation has been designed to course appropriate quantities of uncontaminated air into each mining section. Contaminated air from each section is collected in a return airway and exhausted from the mine without passing through other active mining areas. We know that proper ventilation is a practical answer. Ventilation not only dilutes radioactive contaminants, but also minimizes radon daughter ingrowth potential. The occupational hazard from lung cancer among uranium miners can be avoided, but never before in the history of mining has there been so great a need for teamwork, between management and employees to combat this problem. Control of this health hazard is within our grasp. We can and must meet this challenge.